Okay. By the way, this LC3B was the first machine where I learned computers really from. And I think it's very fascinating to understand the basic principles by working with a small thing. Because all the principles are the same. If you go and build a complicated x86 processor, it's going to be very similar. If you understand these basics, you should be able to build anything complicated. Okay. So no questions, so I'll continue. So I already said this, so required readings this week, next week. So this is the agenda for this part of the lecture. Basically, we're going to cover hardware description languages. We're going to look at how to implement combinational logic. We're going to implement how to implement sequential logic. So all of the constructs you've seen, now we're going to implement them in a language. So this is really a tutorial in my view. Also, I'll give you my perspective on how to program better. But we will not really cover all. And there will be some slides I'll go over quickly because it's programming in the end. The best way of doing programming is really you going and doing it and understanding it. I'll give you the basic concepts mostly over here. But all slides will be beneficial for your labs. So it's really important to look at it. Okay, so let's start with the motivation. Basically, we want hardware description languages. Why do we want them? Because we want to actually build complicated stuff like this. So this is already old. It's 2017. We should update these slides at some point. So this is a 64-bit processor. It has basically data path elements where you can operate on 64 bits. It has 4 cores, 8 threads. A lot of you probably are using this or something newer or something better. It has pipeline that has 14, 19 stages, which you will also learn about later. But basically, it has a lot of stuff in it. And it's already obsolete, if you will. This is not the latest generation. But basically, it's complex. It's not simple. And it doesn't look simple. And if the parts that look simple are memories, of which you need a lot, because you need to deal with a lot of data, the parts that are complex are actually pretty complex. And you will see the complexity in the remaining lectures, like how to design. So the key question is, how do you deal with this complexity? And hardware description languages are the way to program it. If you were actually doing finite state machine design by hand for this processor, good luck with it. You could do it, but it may take years and years. So we want to program this, basically. We want to automate this process. And that's where hardware description languages come in. You need to be able to specify these complex designs at a higher level of abstraction, communicate with others in your design group, because one person is very difficult. I guess if you are able to do a Kaby Lake with a single person, I would applaud you quite a bit, but it may take you a lot of time. These design teams are usually much bigger. Like Intel employs, I don't know, 500, 600 people to do the design overall. I'm not including the verification part. And we want to simulate the behavior of this design before we implement it. Because we want to figure out if the design is buggy or not buggy before we implement this in hardware, because hardware implementation is extremely expensive. Right? People actually build fabs for billions and billions of dollars and Swiss francs, whatever your currency is, to be able to do this at high speed. So, okay, basically, is it what I want to build? And of course, we want to automate parts of the process. This is called synthesis. We want to write code in some high-level language and press a button, and automatically some part of the circuit, hopefully all parts of the circuit, gets generated. Now, this is nice if you actually, people have tried to do this with very, very high-level languages like C or Java. You write a program in Java, you press a button, and magically, the hardware gets generated. All of the finite state machines get generated. Good luck with that. People have been pursuing that for decades and decades, maybe 4 decades or more. Unfortunately, it's not been very successful. That's why we need a lower level of abstraction. And that's where hardware description languages that are specialized for hardware design, come in. So, but if you can do the synthesis, then you can also hopefully automate, make sure your synthesis tools are really good and bug-free. And as a result, you can go from the hardware description language to hardware without bugs. So that's actually nice. In modern processors, actually, the cutting-edge processors, a lot of the parts are automatically synthesized like this. There are some parts of the circuits that require very custom logic, where the designer needs to go in and actually lay out the logic themselves, because those are very performance critical. And the synthesis tool is not good enough to be able to do this automatically to meet the timing requirements that we will discuss in the next lecture. So most of the design we want to be automatically synthesizable. And that's why we want hardware description languages. And there are many of these. The 2 dominant ones today are Verilog and HDL. we're going to cover Verilog. VHDL, the book covers both, actually. If you want to learn both, you can look at chapter 4. Well, you should look at chapter 4 over here. But it's not easy to learn the other one if you already know one. And you can switch between them also. And a lot of the mapping is mechanical. If you actually learn one language, it's very easy to learn another language. And you will see that Verilog is actually similar to some higher level languages like C as we go over it. How many of you know Verilog here already? Okay, how many of you know VHDL? Okay, some, but not as many. That's what I expected also. Actually, I didn't expect everyone to know about anything over here. So, okay, but you will learn. That's why this is the introductory course, right? So there are two well-known hardware description languages. I'm going to go through these very quickly. You can read the history somewhere. It's not important. What's important is what you do with it. So clearly, this is Verilog, blah, blah. You don't need to know about this. But basically, this is older. But somehow, I think Verilog has surpassed. I don't know, maybe the tools have been better. There's a historical thing. So that's why we're going to use Verilog. If you go to like these top-notch companies that do hardware design, which is pretty much all companies today, even the traditionally software companies are doing a lot of hardware design today, like Google, Facebook, these big internet companies, Microsoft, Amazon, who are actually traditionally software companies. They're all doing hardware design today because they're limited by the performance and energy efficiency. And they're all using languages like this, based on Verilog, for example, but they add stuff internally, like internal libraries, so that they can ease the design that they do internally. Okay, so we're going to look at Verilog. Basically, the designs it's going to be very much similar to software engineering. Basically, we want designs that are hierarchical, right? You don't want designs that are like a mess, that do not have modules. So we're going to build hierarchy into our design because the design is complex. So if you look over here, it's kind of like hierarchical also. So if you have, let's say, a shared cache component, and then cache component consists of smaller arrays, and arrays consist of gates in the end. So basically, we're going to instantiate small stuff and then build up. Basically, there are some predefined primitive gates that we will have, as I will show you in the syntax. And we'll build simple modules by instantiating these gates. We'll build muxes, for example, by instantiating these gates. And then there'll be a module, and then we'll build bigger modules from these smaller modules. And hopefully, you'll have a top-level module saying, this is my processor, tabulate. Okay, so hierarchy is important because it controls complexity clearly. This is very similar to functions in software, right? If you didn't have function calls, modules in your software, it would be a nightmare to program and maintain. So complexity is a huge problem. Actually, hardware designs are very, very complex today. They're getting even more complex. Okay, you can read this on your own. That's what it says. So, okay, there are two design methodologies. And I think the good design methodology mixes both in the end. I've seen this many times. Top-down is good to begin with, but sometimes you want to do bottom-up also, and you want to meet in the middle. So top-down means you start with a top-level module and identify the sub-modules necessary to build the top-level module. This is a processor, and then you say cache, pipeline, and I don't know, input-output, right? You can, that's one way of doing the sub-modules. And then you divide the sub-modules into sub-sub-modules, sub-sub-sub-modules, until you get to the leaf cells. So leaf cells are circuit components that cannot be further divided, or that doesn't make sense to be further divided given the abstraction level you choose, like logic gates, cell libraries. So if you may have leaf cells in your cell library saying this is a register, right? And you don't want to divide the register, you just pick the register that satisfies your design points like performance, energy. We will see that this could be AND gates also, right? So this really depends on your library in the end. And the higher the level of abstraction and the ability for the designer to choose, the better, because they can now make, they can be more productive, right? The lower the level of abstraction, if the leaf cell is a transistor, which is not going to be in any of the languages, the leaf cell starts with the logic gates, then it's a bit harder, right? So bottom-up design methodology goes basically the opposite way. You first identify the building blocks that are available to us. And actually, this happens today also. Basically, people say, okay, these are the common building blocks that we want when we want to design. Muxes with different properties. I don't know, you could have blocks of memory with different properties, and these are our leaf cells, and some gates also. And then you build the sub-modules, and then sub-modules, and then sub-modules on top of them, and then you get to the top-level module by combining them. So usually top-down and bottom-up meet. Usually you start with a top-level design module, and then you break it down into pieces. And then you also usually have some libraries at the bottom. We'll see there are some basic functions that are provided by Verilog, but you could build libraries on top of that, and then you could meet in the middle and design your modules. Okay, so what's a module? Module is the main building block in Verilog. You first need to define the name of the module, hopefully. It's like a function, as I said. And then you have the directions of the ports, inputs and outputs. It's like a function, as you can see again. And the names of the ports, basically the name of the arguments of the function. So hopefully it's clear, basically. And then you need to describe the functionality of the module, which is even the more interesting part. But you need this interface so that you can connect the submodule to other modules, right? So let's take a look at this one. So this is basically how you define a module in Verilog. It's not the only way, we'll see other ways. Basically, these are your inputs and outputs, and then you specify your inputs and outputs. Well, I guess I'm going to have an animation. The name of the module is important. You have the port list, and ports have a declared type. They cannot change types. And that's the way to actually define it. How many of you have done it already in your lab? Okay, good. But some people haven't. So it's simple. I mean, if you know programming beforehand, which is the assumption of this course, you should be able to do this relatively easily. So these two are functionally identical, as you can see. Basically, you can, in the list of inputs and outputs, you can basically specify directly inputs and outputs. This is a matter of style, and if you're working for yourself or a company, it's always good to follow a style. The coding style is important because that improves code readability. I mean, good software engineering principles apply over here also. You don't want to mix this and this. It's good to be consistent. I don't know which one's better in the end. Sometimes this is better, sometimes this is better. Okay, so you can have multiple bit inputs and outputs. This is called a bus. And then how do you define it? Basically, you provide the number of bits. That's the end of range and start of range. The best way of learning this is by through example. I can give you a lot of definitions, it'll be boring. So let's take a look at an example. This is a 32-bit bus, A. This is an 8-bit output. This is an 8-bit other output, B1 and B2, okay? And this is a single signal, basically. So A represents a 32-bit value in this case. We prefer to define it that way. You could also define it this way, but that's, again, this is a convention. I find this a lot easier to follow. The least significant bit is over here, and the most significant bit is over here. So but it's good practice to be consistent with the representation. Either you use always this or always this. If you actually mix them, now somebody looking at your code who's never seen the code becomes very confused, right? So it's better to be consistently consistent in what you choose. If there are two ways of allowing it, use one consistently. And by that same token, if you're wrong, be consistently wrong. Because if someone figures out that something is wrong, they can flip the bit and change everything to be right. If you're inconsistent in how you're wrong, that's a problem, right? It's harder to fix. Okay, so let's take a look at manipulating bits. So you can do bit slicing, which is this. Basically, you have a long bus, and you have a short 8-bit bus. Basically, you can assign 8 bits to the short bus by slicing some bits of the long bus. Basically, the 8 bits here get bits 5 through 12 of the long bus. Okay? You can pictorialize this, but I think it's simple. You can do concatenation. Basically, what this does is it's a 4-bit bus wire, Y. It basically, you basically concatenate these 4 bits. 0th bit of A, 0th bit of A, first bit of A, and second bit of A. Okay? And A is some input, which is not here. Makes sense, right? It's simple. And you can do, you can actually have multiple copies like this. This is, if you actually want to replicate 0th bit of A, bus A, into 4 bits, into a 4-bit bus, this is what you have. For example, if the 0th bit is all ones, this will get values 1, 1, 1, 1. And this is another way of simplifying it. Basically, this has 4 copies of A0. Okay, so hopefully this is simple. I'm probably spending a lot of time on something simple. Okay, so let's, Verilog is case sensitive, like many languages. Okay, names cannot start with numbers, white spaces are ignored. You need to follow some convention. You need to, unfortunately, have syntax in the language. If you raise the level of abstraction, I think you can get rid of syntax more or less, but there will be some level of syntax at some point. And then you can have comments, as you can see. And commenting your code is really important. because I don't think there's anyone in the world who can magically understand code that's extremely complex without comments. Some people are extremely good at it, but okay. So there are two main styles of this important hardware description language implementation. One is structural. This is gate level. Basically, you define gates. The module body contains gate level description of the circuit. And you describe how the modules are interconnected, and each module contains other modules and interconnections. Basically, you specify everything at the gate level. This describes the hierarchy. Behavioral is, the abstraction level is much higher. Basically, the module body contains functional description. We'll give examples of this. It contains logical and mathematical operators. For example, you can have equal signs. That equal sign is not a gate level description because there is no equal gate. You build the equals from gates, right? And in this case, the level of abstraction is much higher than the gate level. So there could be many possible gate realizations of a behavioral description. And practical circuits usually use a combination of both. We will see later that ideally we would like the code to be synthesizable. There are some constructs that may not be synthesizable if you go a very high level of abstraction. That's why you mix both of these. Okay, so let's take a look at structural HDL, hardware description language. So this is a module that consists of two small modules. Let's assume that this is our top module. And I'm going to construct it very quickly, very simply. It's very simple, actually. You basically show your top module, the inputs, and then define a wire that's connecting the inputs, and then the small modules over here. As you can see, that's the wire. And you instantiate the small module once. This is the small module description. And you instantiate it over here inside the top module. Basically, you connect the A input to A over here, the B input to cell over here, and then the Y output to the wire N1. Okay, now that's your module, that's it, this is done. There must be some description over here, of course, as to how the module is done. And then you actually instantiate the second one also by connecting the A input to N1, and then the B input to C over here. It's very confusing, but this is how you actually need, this shows you the importance of labeling your inputs and outputs nicely. And the Y output to the Y output over here. Basically, you're saying the A input of this module is connected to M1, B input of this module is connected to C, and then the Y output is connected to Y over here. Okay, this is one way. There's another way. Now, if you look over here, we basically didn't explicitly specify what A input, B input, and Y output should be connected to. We just said A cell M1, A cell N1, A cell N1. So this is assuming that the order is the same as the definition in the description. You could do it. I wouldn't recommend it. It's not very nice because if you actually make a mistake over here in the order, then basically the circuit will be messed up. Right? So this is a shorter instantiation. That's for convenience. But I would suggest it's not good practice because it reduces code maintenance. This is maybe cumbersome, but it's much more clear. Yes?
Can you mix and match with structural and behavioral within one module?
Yes, absolutely. We'll see examples of that later.
Also applies.
Yeah, if it improves code readability, sure. Absolutely. Okay. Okay, so let's take a look at structural example over here. So Verilog supports basic logic gates. I think I already said this earlier, but basically let's take a look at how they are. So these are the predefined primitives. They're instantiated like modules, except that they're predefined in Verilog and do not need a module definition. By the way, let me say that you're basically limited by what your compiler can support. If your compiler can compile, it can do anything, basically. Does that make sense? If you have a poor Verilog compiler, then you may not be able to mix. But hopefully the state-of-the-art compilers are much better. Okay, let me go back over here. Basically, this is one example. This is actually a mux. You remember the mux, multiplexer, a two-input mux, D0, D1, select input and the output. And it basically consists of the NOT, AND, and OR gates. And you can convince yourself this is a mux. This is very similar to what we've seen in the mux. So these are primitives that are defined in Verilog. So you don't need to define NOT, AND at a lower abstraction level. You can use these. Okay, let's take a look at behavioral. So remember, behavioral is the functional description. At level abstraction is higher. Okay, so if you look at the behavioral, this is one example circuit I didn't show you earlier, but this is exactly the behavioral description. You basically have the NOT of A and NOT of B and NOT of C, or there's some precedence over here, these. Clearly, you didn't say there's a NOT gate, there's an AND gate, there's an OR gate, but it's clear that the circuit actually gets synthesized to something like this. So this is actually the synthesized version of the circuit. Okay? You've described the circuit at a much higher level of abstraction than gates here, with logical behavioral operators. Okay, so this is another, basically these are bitwise operators in behavioral Verilog. So you can see that the inputs are 4 bits, outputs are 4 bits, and this is how you do bitwise AND, bitwise OR. Bitwise means bit 4 of A gets ANDed with bit 4 of B, sorry, bit 3. And then bit 2 of A gets ANDed with bit 2 of B, bit 1 of A gets ANDed with bit 1 of B, and then bit 0 gets ANDed with bit 0. And then the results are stored respectively in bits 3, 2, 1, 0. That's bitwise, right? And similarly, you can do XOR, NAND, NOR. It's nice. And then this is the circuit that you get if you synthesize it. Okay, so you can also have reduction operators. This is an example. Basically, this is the AND of all bits of A. Remember, you see that A is an 8-bit bus. Basically, you AND all of the bits. It's much easier to write than this one, clearly. Right? And this is also easier to write than having AND gates over here. Okay, and this is the synthesized version of it. So basically, in the synthesized version, this is the inputs, outputs, and this is the combinational logic over here. We'll see other logic later. Okay, this is another way of doing mux. I showed you the mux with the AND NOT gates earlier, right? And this is the mux at a higher level of abstraction. How many of you know this sort of thing? Okay, nobody? Okay, some people know, that's good. So this is common in higher level languages. C has it, other languages have it. Basically, this says that if S is true, then Y gets assigned D1. Otherwise, Y gets assigned D0. Y is a 4-bit output, and these are the 4-bit inputs. So this is a 2-input mux where each input is 4 bits and output is 4 bits. Much easier, as you can see, than gate level description. And this is also synthesizable. You can give this to a tool, and it generates this mux for you. A nice tool, of course, yeah. Okay, so this is also called a ternary operator. It operates on 3 inputs, and it basically gives you an if-then-else construct. If you know about it, it's nice. So now it's becoming very similar to any programming language that you may know of, right? In the end, it's a programming language. Okay, so now you can build a 4-input mux with this, basically. This is a 2-input mux that selects between D3 and D2. This is, again, a 2-input mux that selects between D1 and D0. And this is another 2-input mux that selects between the output of this and output of this, using another bit, of course. Right? So this is a 4-input mux. Based on the values of 2 selects bits, you choose one of the values out of the 4. Let me finish this thought, and then we'll take a break. So this is another way of doing conditional assignments. So basically, this is another way of doing the 4-input mux. As opposed to using the ternary operator, you can check if the 2-bit inputs are 1, 1, then the output is D3, 1, 0, 0, 1, otherwise the output is D0, right? That's another way of doing it. Let me cover the precedence, and then we'll be done with this part. So clearly, you can do the mux in different ways. So precedence is interesting. Somebody asked this question earlier in an earlier lecture. Clearly, there's a precedence, like in any language. Some operators are higher precedence compared to some operators. Lowest one is ternary. That's why we're able to do this without using parentheses over here, right? The ternary operator has the lowest priority over here. Okay, so you can study this. In general, I would not suggest relying on this because I get actually confused. Like if you ask me, I don't know if this is lower priority than this, or this one is lower priority than the other one. So if you properly parenthesize your code, it's much better in general, but you can see that it becomes cumbersome with very large equations, right? In that case, it's better to break the equations into smaller components. Okay, I think this is where we will pick up when the bell rings, and we will continue Verilog. All right, let's continue. Since we want to finish Verilog today, are you having fun with Verilog, by the way? Is it good? Cool. It's a different type of programming language, and actually one of your colleagues over here made a good point that I'm going to repeat over here. It's not as similar to other languages. You're used to programming with functions, right? This module is kind of like a function over here, except the return value is not there, right? The return value is actually somewhat encoded here. basically the function's output, you can think of it as the return value, is y, and you connect the output to the wire N1 that you declared over here. Basically, you can think of these as return values, but you need to connect the return value to an output. And the inputs are arguments to the functions, and you basically connect the inputs to the parameters, input parameters of the function. You can think of it as like you flatten the function and ensure that the parameters are connected to certain wires or inputs, and the outputs are connected to certain wires or outputs, basically. Okay? I like that, I think. That's a good way of thinking about it. Okay, now let's skip these because we've already done all of this. So we were precedence, yeah, precedence, I think in general it's not good to rely on precedence, but sometimes, like and takes or, precedence over or is common in many languages, I think, so that sometimes you can rely on. Okay, so if the compiler is not correct, actually it will not obey precedence, and sometimes it may not be good to trust all the compilers of the world. Okay, how do you express numbers? This is a bit boring, but it's important. Basically, you specify the number of bits. Well, clearly we said it specifies how many bits are used to store the value. Specify the base. So you may want to have a hexadecimal, binary, decimal, or octal. You specify the number after that over here, the value expressed in the base. Don't forget that over here whenever you specify the number of bits. That's required. Okay, you can also have x invalid and z floating as values. I will show you z again. We've seen z. X is invalid, basically. You don't want x's in your design, actually. But you can have them to describe what happens when you operate with z inputs. Okay, underscore can be used to improve readability, like that over here. So this specifies an 8-bit binary number that has this value. So okay, this is an example. Your book has some other examples. Default is if you don't specify how many bits you have, you get 32 bits by default. And you may not want that, right? You may not want a 32-bit value wire. Okay, I mean, you can study this. It's kind of obvious. So a reminder, this is a reminder. Floating signals we covered. I'm going to go through it relatively quickly again. This is a signal that's not driven by any circuit, if you remember. It's also called an open circuit or floating wire. It's also known as high impedance, high Z, tri-stated signals. And this is one way of implementing that in Verilog. So this is a tri-state buffer. If you remember the tri-state buffer, I'm going to show you the truth table in the next slide, but I've already shown you that. Basically, it's a 4-input tri-state buffer. Y gets assigned to the input if the enable signal is 1. Otherwise, the output Y gets 4 Z values, meaning it becomes Z. Z means unknown because this wire is not driven by anything if this tri-state buffer is not enabled. And if you recall, this is a slide exactly from the previous lectures, one of the previous lectures when we covered combinational logic. It enables gating of different signals onto a wire, and this is a truth table. And the previous Verilog code implements this truth table, basically. And if you remember, why is this useful? I told you one example is a wire that's connecting the CPU and the memory, a bus. At any given time, only the CPU or the memory can place a value on the wire, not both. And you can use 2 tri-state buffers to implement this. One driven by the CPU and the other memory, and ensure that the logic or FSM that you're designing enables at most 1 at any given time, right? And I've given you a high-level picture of this, right? This is, at the very high level, it looks like this. CPU, memory, and you ensure that only one of them drives the shared bus. And if you remember the LC3 design, it had a bunch of these tri-state buffers, and we will see that even more. So keep this in mind. This is a very important and useful construct. We'll see it tomorrow also, actually, in the timing, because it turns out if you do designs with tri-state buffers, they can be really, really fast. We'll see a MUX tomorrow, multiplexer that's designed using tri-state buffers that's much faster than a MUX that's designed using gates. Well, this is a gate also, but using more complicated AND and OR gates. Okay, so this is another, this is just for your fun. This is a truth table of AND that has 2-input AND, A and B, single bit. But we extended the truth table with Z and X also. So this is the regular truth table that you would have with AND. The result is 1 only if A and B are 1. But what happens if A and B can take values Z and X? Well, AND is nice. If one input is 0, it doesn't matter what the other input is, you'll get a 0. So that's nice over here. But if one input is Z and the other input is 1, basically you get undefined invalid values because you don't know what that floating value is. It's not driven by anything. So this is the part of the design that you should definitely avoid. You should never get into this part when you're designing. And you need to ensure that by ensuring that the z values never mix with logic values over here, and hopefully you never have x values because you want to avoid them to begin with. Okay. So now we've seen some basics. Let's talk about what happens with the HDL code. Remember, we want to actually make ourselves efficient in designing hardware. So synthesis is what happens with HDL code. That's one thing that happens. Basically, you have modern tools called synthesis tools that are able to map hardware and description languages code to low-level cell libraries. But not all kinds of hardware description language code. There's a synthesizable portion. And this depends on what kind of tool you use. There are some synthesizable constructs. There are some non-synthesizable constructs. If you do gate-level structural Verilog, everything's synthesizable. Most of behavioral Verilog is also synthesizable. But if you go fancy, it may not be synthesizable. Because now your tool needs to actually figure out what kind of low-level circuit it needs to generate based on the description you have, right? You have some hardware description. So somebody also in the break asked the question, will the circuit that's generated by the code, the structural Verilog, be the same as the circuit that's generated by behavioral Verilog? Not necessarily, because behavioral Verilog is at a much higher abstraction level, and the synthesis tool may actually take that abstraction level and pick different gates to satisfy the specification in the description. Whereas if you already specify the gates exactly, the synthesizable tool will take those gates and basically generate the hardware for you. Okay? So that's the difference between also a behavioral versus structural. Structural Verilog, you can clearly define your circuit at the lowest level almost. So these synthesis tools can also perform many optimizations. If you basically, for example, have that multiplexer that's designed using the ternary operator, remember the question mark and then the colon, then it can actually give you a multiplexer that's really fast. Whereas if you actually design a multiplexer with gates that is not fast, it'll probably give you what you actually defined. Because your level of abstraction is much lower, and now the optimization depends on you, not the synthesis tool. Okay, but they cannot guarantee that a solution is optimal, and this is a very tough problem. It's actually an NP-complete problem, which is very hard for computers to solve. Basically, the computer, what the synthesis tool needs to give you is what's called a netlist. Netlist is essentially a description of all the gates and wires in your circuit. It's called a netlist for historical reasons. That netlist, it needs to lay out the code and place all of the gates and route the wires. And to be able to do that, it uses some algorithms internally, and those algorithms are not very easy to optimize. Okay, and this is the most common way of digital design these days. You write Verilog code and you give it to some software algorithms and they generate the netlist, and then that netlist somehow gets transformed to real hardware. But this is basically the specification of the hardware. And most companies use these tools to improve productivity. But there are some parts, as I said, that are really performance critical, that no synthesis tool generates efficient or fast circuits. As a result, you need to do it by hand. Hopefully that's not a large fraction of your design. So with hardware description language code, you can do simulation also. As I said, simulation is very useful because you can test whether your circuit behaves correctly as you want it by doing simulation. You don't want to directly synthesize this, perhaps, and generate hardware. You want to first simulate and test it, and we will see that. This allows the behavior of the circuit to be verified without actually manufacturing the circuit. And simulators can work on structural or behavioral hardware description languages. So let's take a look at an example very quickly. We will talk about testing later in this lecture. Basically, this is a simple example that I showed you, behavioral code. This is the synthesized circuit. So if you give this to a synthesis tool, it will probably generate something like this without much optimization. And this is very low level, as you can see. Okay, and this is a simulation of it. Basically, you can run a tool on this, change the inputs, and then observe the outputs in a waveform. And you will do this in your labs, and this is the waveform diagram, and hopefully now you can test, if I change all of the inputs to 1, am I really getting the output that I expect? So simulation is very useful for that purpose. Okay, so basically this is what we've seen so far. We've described a structural hierarchy with Verilog, instantiating modules, describing functionality, writing simple logic equations. I think I'm going to go through this very quickly. and constants, but there's more. Basically, we're going to look at some more Verilog examples. You can write Verilog code in many different ways. Some of it is readable, some of it is unreadable. So at the very low level, you have poor readability, but you get more optimization opportunities, especially for low-level tools sometimes. But sometimes, higher level, you have better readability and limited optimization opportunities. So let's take a look at readability a little bit. So basically, we will use our gates to look at different ways of having a 4-bit comparator, essentially equality checker. Are these two numbers that are 4-bit, each represented with 4 bits, are they equal? So we're going to use these building blocks. This is our XNOR gate, which is used for comparison. It's basically a bitwise XNOR. Basically, it's a NOT of the XOR. And we're going to use an AND gate. And we're going to look at different levels of abstraction and how readable they are. So you don't need to fully understand exactly how this operates, but you will see the complexity of the code. These are basically our XNOR and AND gates, and trust me that this is a comparator, basically. The result is equal if the 4 bits are equal. This looks horrible, right? I mean, if you want to reverse engineer and figure out this is a comparator, you can do it. It will take time to do it. Okay, but now we're going to simplify it. So this is a gate level implementation. It's the lowest level of abstraction. Now you can do logical operators, get rid of these ANDs, and have these logical ANDs. And then you can make them actually multi-input ANDs, so get rid of the intermediate signals. Now we've actually clearly you can see that there's a 4-input AND gates, right? That's nice. Now you can have multi-bit signals, as opposed to having single bits over here. You can have multi-bits, 4 input A, 4 input B, output is one bit. So, and you remember this is a bitwise AND of all elements of C. That's nice. Now we're going to simplify this part. Let's simplify that part. So XNOR is actually, you can get rid of all of these XNOR gates and have a bitwise XNOR over here. Nice, right? It's much cleaner now. And even this is not the highest level abstraction. This is the highest level of abstraction. This is much better, right? If A is equal to B, return a 1, otherwise return a 0. Now I can understand it. Anyone who looks at this code understands it. So that's the difference between structural and behavioral. This is the highest level of abstraction you can get. Okay, so this is clearly more reusable also. But you haven't optimized your code by hand at this point. Now you're at the mercy of the tool. If the tool has a very good implementation, that's nice. If the tool doesn't have a very good implementation, not so good. Okay, basically, what if you want to actually generalize this to 5-bit number comparison, 6-bit number, n-bit number comparison? You don't want the same function repeated for 4 bits, 5 bits, 6 bits. So what do? Basically, we parameterize the modules. So hopefully this is clear. You can have module parameters. It looks like this, basically. You have a parameter that you define width of the multiplexer in this case. And the multiplexer, by default value is 8, but you can change it. You can make it 16, you can make it 5, and basically it works with all different parameters width of the wires. So hopefully this is obvious, right? You don't want to have different modules for 4-bit, 2-bit, 3-bit muxes. Okay, I said that. You need to set the parameters for different values when instantiating the module. So let's take a look at an example. This is our module. And this is, if you use the default parameter, you don't need to specify the parameter. If you want to have a 2-input mux, where each input is 12 bits, this is how you instantiate it. It's a bit cumbersome, but that's the syntax Verilog folks chose. Basically, it's a 12-input mux. No, not 12-input mux. It's a 2-input mux with 12-bit inputs. This is a more verbose version. You clearly specified this is the width, right? It's actually nice, I think. I like this better because I can understand this better, right? Whereas here, you really need to know the syntax. If you're an expert, clearly this is not a problem, but if you're a beginner, I would suggest using this. And in general, it's not bad because this is more complete, right? And we already discussed these, right? You don't need to know the order over here or ensure that the order is correct if you actually have clearly specify what input is connected to what wire. Okay, what about timing? We're going to talk about timing. You can possibly define timing relations, but these are only for simulation. They cannot be synthesized. We will see that. Timing is the subject of tomorrow. But these are used for modeling delays in a circuit. So for example, you can basically assign a time scale, say that this takes 1 nanosecond, and then basically you change this statement takes effect after 5 nanoseconds over here, after 5 time steps. So if you're debugging the code, it's good to add this stuff. This output is supposed to change after 9 time scales from this. Okay? So if you're debugging the code, you can actually do this kind of time, have this notion of time. And this has nothing to do with timing, but we'll get back to this when you're testing your code. This has nothing to do with how long it takes to really, for the signals to settle in real life. We'll cover that tomorrow. Okay, good practices, consistency is important. This is, I think I said a lot of these, but I didn't say this. Define one module per file, that's good, because your hierarchy management becomes easier. Use a file name that equals the module name, that's also good. Assuming your module names are nice, this is good. And Verilog describes hardware, always keep that in mind. So it's not, the difference from other programming languages, Verilog is very concurrent. So if you actually master hardware, you're very good at concurrent programming and parallel programming. You will understand that because a lot of things happen at the same time, and we will see that. Okay, so this is a summary of what we've seen for combinational logic so far. Basically, I've discussed Verilog, structural and behavioral, and showed combinational logic constructs. So we're missing something, and that something is sequential logic. Right? And this is important, so we're going to go through sequential logic now. Hopefully this will be fun, and it's going to be easy, but the constructs you need are going to be different. So we're going to cover sequential logic and then develop test benches. Any questions before we go into sequential logic? You'll see all of this during your labs, and it'll be a lot of fun. Basically, you remember sequential logic is a combination of combinational circuits and storage elements. You can think of it that way. And we need to basically have a way of describing flip-flops, latches, and finite state machines. Whatever we discussed in the previous lecture. So you're going to jog your memory a little bit more. So state transition will be triggered by a clock signal, although it doesn't have to be triggered by just the clock, but for synchronous design, remember clock is the synchronizer. You want state changes to happen at the edge of the clock. For synchronous design, you want to trigger the state transitions only at the clock. But in Verilog, you can describe state transitions on any signal, as we will see. You will do a lot of synchronous design going forward, so I would suggest using just the clock to trigger state transitions in finite state machines. Some things that I'm going to describe over here will be asynchronous, in the sense that some of the state transitions will happen maybe with some other input changes, not necessarily clock changes. Right? That's very different design. It's asynchronous design. That's not what we're going to do in the labs, but sometimes they could have their use also, because clock has some overhead, as we will see tomorrow. If you do asynchronous design, you can get rid of that overhead. But you will see this tomorrow because there's some overhead in terms of communicating the clock. Okay, so basically, we're going to trigger state transitions. Remember, the latches are sensitive to the level of the signal. If the signal is 1, then the latches will latch the value and transparently. If the signal changes, if the input changes while the signal is 1, you will see the output in the latch. That's why they're transparent. You'll see the output reflecting the input. Flip-flops, as I discussed earlier in this lecture, also are sensitive to the transitioning of the signal, positive edge of the clock or the negative edge of the clock, but not while the signal is high or low. They're not transparent. They just capture the value when the clock goes from 0 to 1 or 1 to 0. Okay, so basically, combinational logic constructs that I showed you are not sufficient for this. We really need new constructs, and I'm going to introduce 2 constructs. One is the always block, and the second one is the positive edge and the negative edge of a signal. So, okay, what is the always block? Always block looks like this. Always at some sensitivity list, you execute some statement. Basically, this says that whenever the event in the sensitivity list occurs, the statement is executed, otherwise it's not executed. That's how you put memory into your block, right? That otherwise part is memory. You remember what was there before. But when the sensitivity list changes, you execute this and you basically capture the value. Okay, so you can put anything in the sensitivity list, any input. So this is one example. This is a D flip-flop. Remember, in D flip-flop, we have an input Q. In this case, it's a 4-input register. We have an output, 4-input output register, and this is how you define the outputs that have state. It's called reg. Unfortunately, it's reg, but anyway, that's the syntax. Basically, the sensitivity list consists of the positive edge of the clock. When the clock is rising, meaning at the positive edge of the clock, Q gets assigned D. Otherwise, nothing happens over here. Otherwise, Q stays with the value that it had before. That's the idea. And this is our positive edge basically defines a rising edge, transition from 0 to 1. And the statement is executed when the clock signal rises. I've already said this. Once the clock signal rises, the value of D is copied into Q. Now we will see this assignment in a little bit. This is called, anyway, we'll see it. This is called a non-blocking assignment, meaning that you could have many other assignments over here. But this is our simple D flip-flop that we've seen before. Okay. So assign statement, we used the assign statement before, right, for wires. We don't use it within the always block. Always block is a bit simpler like this, because it's not a wire, right? This is really a stateful element over here. And this is the non-blocking assignment, basically. So we will see the difference, this less than or equal to sign. It's really not less than or equal to, it's really an assignment. Maybe unfortunate syntax, but that's how it is. And we will see the difference between blocking and non-blocking soon. So if you want to have this D flip-flop, you need to declare the assigned variables as reg. So that's a stateful variable. As I said, this doesn't mean that the value is a register. It could be, but it doesn't have to be. It's basically an assigned value. It has nothing to do with the register construct that we've seen earlier. It's just said that, it just basically specifies that this is a value that you assign to and stateful. So we will see examples later again. So let's take a look at asynchronous and synchronous reset. So this is a case where you may, so how do you reset the flip-flop? This is something we didn't talk about a lot before. I'd like to talk about it within the context of Verilog. So you basically use a reset signal, right? Remember the state machine where we had a reset signal? You want to go to that state when the reset is active? That's exactly what we want to do. And we use this to initialize the hardware to a known state, usually activated at the system start. When you turn on your computer, the first thing that happens is actually all of the things get reset to whatever values they need to capture. 0, 0 usually, but doesn't have to be 0, 0 also. Okay, so there are two kinds of reset. One is asynchronous, synchronous. Usually, remember, clock is the synchronizer. That's the great synchronizer. It synchronizes everything. Asynchronous means you don't have a clock, or you don't respect the clock. Basically, in this case, the reset signal doesn't respect the clock, or the flip-flop doesn't respect the clock, in the sense that the reset signal is sampled independently of the clock. It gets the highest priority. This has issues, because if you do stuff without respecting the clock, you may have issues like glitches, metastability, which we will talk about tomorrow. But there are cases where you use asynchronous reset also. So synchronous reset, basically you respect the clock. The reset signal is sampled with respect to the clock, and the reset should be active long enough to get sampled at the clock edge. Again, this is dependent on the lecture that we're going to see tomorrow. But this results in a completely synchronous circuit. Basically, everything is governed by the changing of the clock, okay? And that's what most circuits are today, but there are some asynchronous components. That's why I want to cover this a little bit. Okay, so this is one example where the reset is asynchronous, meaning that whenever reset changes, the flip-flop gets reset, or some value in the flip-flop changes independently of whether or not the clock changes. So how do you do that? But basically, if you want an asynchronous reset, you declare the reset also in the sensitivity list. Remember, this was our flip-flop, D flip-flop, just looked at positive edge of clock. Now we're going to also look at negative edge of reset. And this statement gets executed. Well, I think basically in two cases, two events can trigger the execution of the statement. A rising edge on the clock or a falling edge on the reset. Basically, whenever the reset goes from 1 to 0, this gets triggered also. Now, what this does is, if the reset is equal to 0, it sets the value to 0. And you may want to use this to reset the flip-flop, right, to zeros. And you basically maybe use the reset only when you start up the system. And the rest of the time, you don't change the reset value. Everything else is governed by the clock. But if you have some glitch in your reset signal, then you have a problem, right? Everything in your machine can get reset, and you may get a blue screen. I don't know if that still happens. I don't use Windows these days, but okay. Okay, basically, for longer statements, so this is another thing that I will introduce. Begin and end pair can be used. You don't need it in this case, because if and else is enough, and you know that that's the whole thing that's executed. But if you have a long statement, begin and end is useful. In general, it's good to have begin and end statements to demarcate the beginning and end of the always blocks. Okay. So in this case, if reset, first you check the reset, as you can see. If reset is 0, Q is set to 0 whenever this gets triggered. And as I said, this independently of the clock. Like if there is no reset, the regular assignment takes effect, which is what you've seen earlier. Q gets D. Okay, so this is the flip-flop with synchronous reset. Synchronous reset means you reset the flip-flop only on a clock edge. So we get rid of the negative edge reset from the sensitivity list. We just respect the clock all the time. This is a very good design, synchronous design. In general, it's less buggy, or probability of bugs is less in this case. So if reset is equal to 0, Q gets 0 when you sample it at the positive edge of the clock. Otherwise, Q gets D. So you just need to control the reset signal whenever you want to reset. That's it. Yes, there's a question? Yeah. Okay, I cannot see you very well. Yes?
Is there a difference between the quality reset is equal to 0 and slightly more?
Oh, like this one and this one? No, it's the same. Okay, we will make it consistent. You found a case where things are not consistent. So it's basically the same. This statement and this statement is the same. Because it's a single bit signal, right? Okay, so that's a good catch. You can be a good hardware designer. Okay, so basically if the reset is 0 here, you get, okay, basically reset happens only when the clock rises here. If the reset changes when the clock doesn't change, then this reset doesn't take effect because the always statement doesn't get executed if the clock doesn't change, right? From 0 to 1. So this is synchronous with respect to clock. Okay, so let's take a look at some other signal, enable signal. So this is a D flip-flop with an enable signal also. So if you want to actually protect your flip-flop even more, such that you want to ensure that there's another signal, right enable signal, this is how you do it. Basically, you don't always, at the positive edge of clock, assign D to Q, but you check enable first. If it's true that enable is set, then Q gets assigned D. That's the idea. So this flip-flop has an enable and a reset, and the reset is asynchronous, as you can see over here. It's an asynchronous reset. And enable signal is not in the sensitivity list. So enable signal is sensitive to clock and reset only, but if reset is 0, then this is true. And Q gets D only when clock is rising and enable is 1. And you can analyze that circuit. Okay, so hopefully this is obvious. And this is our D latch. So I've shown you the D flip-flop. Let's take a look at the D latch. So D latch, remember it's level sensitive. Basically, whenever the clock is 1, and D changes, D is 1, this is what happens basically. If clock is 1, Q gets assigned D. Latch is transparent when clock is 1, in this case. There are other ways of designing it, but this is one way of designing it. Okay. Okay, so the sequential statement so far. Within an always block, please read chapter 4. I'm going through some of these very quickly, but you'll do this by experience. Sequential statements are always within an always block. The sequential block is triggered with a change in the sensitivity list. That's always at something. And signals are assigned within always block must be declared as register. We saw that, or reg, I shouldn't call it register. And we use non-blocking assignments and do not use assign within the always block. Okay, so this is the basics of the always blocks. So in this case, you can have as many always blocks as needed because these may be very different flip-flops, right? You may have 10,000 of flip-flops. Basically, always at the positive edge of clock, this flip-flop gets D. Always at the positive edge of clock, this flip-flop gets normal. So basically different flip-flops over here. And then you may have wires connecting these. Basically, this flip-flop gets the negated value of whatever value was in this flip-flop in the next cycle, basically at the positive edge of the clock. Okay, clearly this is important. Assignment to the same signal in different always blocks is not allowed. So if you're assigning special over here, don't assign special over here because you will get an error in that case, I hope, if your compiler is good. Because it makes no sense to have 2 blocks assigning to the same register. Okay. Okay, so basically, why does an always block remember? Like, why is it a memory element? Why is it a memorizing element or remembering element? So basically, this is a going back to the D flip-flop. This statement describes what happens to signal Q, right? Q gets assigned D at the positive edge of the clock. What happens if it's not the positive edge of the clock? What value does Q get? Well, this doesn't say, but implicitly, it's the value it got before. That's why it remembers, basically. The value of Q that was captured in the past is preserved or remembered. So it's implicit in the always block definition that Q gets the previous value. You don't explicitly write it clearly, right? Okay, But it's interesting that always block are not always latches or flip-flops. Sometimes they're completely combinational. It's a bit sad, but sometimes you use very complicated combinational circuits using this sort of construct. So let's take a look at it. Basically, if you look at this circuit, the always block gets activated or executed whenever invalid or data changes. So whenever invalid and data changes, the result gets assigned some value. So basically, this is a combinational circuit because when invalid is 1, the result gets gets assigned some value, negated data value. Otherwise, results also gets assigned the data value. And this happens whenever invalid and data changes, whenever both inputs change. Well, what is this? It's a combinational circuit, right? Because whenever the inputs change, the outputs get assigned values, which may change. That's not a sequential circuit because there's nothing to remember over here. You don't remember things. Whenever the inputs change, outputs change. Okay? So the circuit is combinational, the result assign a value in all cases of the if-else block, always. That's where you can, so you need to examine the always block to see if it's sequential or combinational. Sometimes you may want to use always as a combinational circuit. I wouldn't recommend it initially, but there are some complicated statements in combinational logic that where using the always block may be useful. But this is a very powerful construct, actually. Basically, an always block defines a combinational circuit if all outputs are always updated, meaning that all right-hand side signals are in the sensitivity list. You can actually do this, always at star. Basically, at any right-hand side input, any input changes, always block gets executed. And all left-hand side signals get assigned in every possible condition of if, else, and case blocks. Case we will see in a little bit, but it's very similar to higher level constructs. Basically, it's easy to make mistakes and unintentionally describe memorizing elements like latches, even though you may want combinational elements. So your tools will likely warn you. Make sure you check the warning messages. The warnings are there for some reason. Unfortunately, these tools are not as great as they could be, but that's what we have. So always blocks allow powerful combinational logic statements, like if, else, case. So you may want to use this. So let's take have some fun. So is this sequential or combinational, based on what I described to you? Any thoughts? Sequential? Who says sequential? Okay, so one person says sequential. Who says combinational? Okay. Who says sequential now? Okay, more people say sequential. Who says combinational now? Okay, fewer people say combinational. It's sequential, right? Because what happens is you don't have no assignment for not enable. That's true for output A and output B. So if the enable is true, you get some value, but if the enable is not true, you don't get some value, even though your sensitivity list is any input. Meaning that if enable changes, you don't capture that value, meaning that you remember the old value of output B and output A if enable is not true, okay? So that's the way of checking it. Meaning that in not all cases over here, for any input, the outputs are assigned. Okay, you can do the same thing over here. If you look over here, this is a sensitivity list data, but the output depends on enable, and enable is not in the sensitivity list, which means that if enable changes without data changing, these don't get assigned. As a result, this is sequential also. Okay? Okay, so you should think about this a little bit. Okay, so always block is not always practical or nice. This is a mux. And so if this is one statement, this is another statement. Both statements describe the same multiplexer. This is a combinational always block. Result gets assigned in all cases and all inputs change, as you can see. As a result, this is combinational. But this is much nicer for a mux, right? Okay. So if you use the always block over here, it's more work, clearly. So you can use if and else within an always block, and that's very helpful in behavioral Verilog. So you can use case statements also. This is very nice. Basically, whenever some input changes, you check whether the value of data and assign the output to the data value. Okay? So this is combinational, actually, because there is an assignment to segments for all possible values of the data, because there's a default value over here. If the value of data is not any of these cases, then you assign all zeros to it. So this is a combinational logic, as you can see. Okay, so the summary if else can only be used in always blocks. So if you want to use if and else, you should use this, yes?
When do we use non-blocking statements?
We'll get to that. We'll get to that. Okay. And the always block is combinational. I think I already said this. I'm not going to repeat it. And you can use case-x statement to be able to check for don't cares. So if you go back over here, this is specifying don't cares, right? I don't care what the input value is other than these, then the output should be this. Okay. Okay. So, okay, non-blocking and blocking assignment. So you're at the right point. So non-blocking means that all assignments are made at the end of the block, or when you see a blocking assignment, right? So basically, these are concurrent, meaning that this one uses the old value of A, right? Not the new value that is assigned. While this is being assigned, this is being assigned also. Okay, that's the key in non-blocking. All assignments are made at the end of the block, all assignments made in parallel, process flow is not locked. Okay. Whereas this one, blocking, is you make this assignment first, and then you make this assignment after that. So A value is updated before you make this assignment. Okay, so it's strictly sequential, basically, in this case, in terms of the execution of each statement. And the only difference is this less than sign over here. So it's easy to make mistakes over here, unfortunately, so be very careful when you're doing this. So each assignment is made immediately, process waits until the first time is complete, it blocks progress. So this is one example. This is blocking assignments, right? Well, assume all inputs are initially 0. You basically do the assignment. If A changes to 1, let's say, A changes to 1, all values are updated in order. So you basically execute one by one, not concurrently. So P becomes 1, and then this becomes 0 because it's an AND. Now you use the new value of P over here, right? Okay? And then, okay, anyway. So assume the same thing. This is the non-blocking assignment. So here we execute everything in order, so this one got the new value of P, okay? And also this one got the new value of P and G over here at the end. Assume these were non-blocking, all of these are executed concurrently. So you need to think in parallel over here. This is all concurrent, meaning that each statement uses the old value of A and B, or whatever the inputs are, right? Okay? So if you look over here, when S is being assigned, P is still, when this is being assigned, P is still 0. Because remember, this gets assigned at the end of the block. Yes?
When you say they are executed concurrently, could it be that the statement that executes concurrently will get translated into components which are slower compared to the other ones, and then the new value has already been assigned?
We'll talk about timing later, but a good synthesis tool should not do that in this case. Basically, it should ensure that these are done at the end. But yes, there could be dangers over here. Let's talk about timing tomorrow. So logically, this should all of the values should be changed at the end of it over here. Okay, so basically, you can do the calculations over here, but all of these happen concurrently with the old values. So that's why this gets a 0, right? This doesn't get the new value of. Sorry, that's why this gets a 0. This doesn't get the new value of P. Okay, and then after the first iteration, P has changed to 1 as well. As a result, this always statement gets executed again, and now you actually update the new values again. Since the process triggers again, this time S is calculated with P1, and then you can do this again concurrently in the next case. Okay, so let's go over the rules for signal assignment. Basically, we would like to use always positive edge of clock and non-blocking assignments to model synchronous sequential logic. This is actually a very good rule over here. This is what you need to do if you want synchronous sequential logic. And if you want to model simple combinational logic, use continuous assignments like this. That's what I would suggest doing, and not going very complicated in this course. Unless you're a really well-seasoned designer who has experience, I would suggest keeping things simple. Okay. If you want to do more complicated combinational logic, which in some cases you may need to use something like this, basically, always at and blocking assignments, okay? And as I said this already, you cannot make assignments to the same signal in more than one always block or in a continuous assignment, so this is not allowed, as I said earlier, because you don't know what the value will be here, and this is also not allowed, right? Because this is executed in some cases it's executed, which one will, what value will A get? Okay, so let's take a look at testing a little bit. Let's see how much we can cover in testing. Any questions? Okay. Okay, so basically, we're going to look at finite state machines again. You've seen this, I think, 5 times so far. And this consists of sequential circuits, combinational circuits, and output logic. And we're going to show an example of finite state machine. Basically, okay, I said testing. I want to say finite state machine. So we're going to build a finite state machine very quickly. It's very simple. So basically, this is the finite state machine that we want. We want to divide the clock frequency by 3. This is how we implement dynamic frequency scaling in existing machines. You have a clock signal, you divide it by 3. What does this mean? The clock signal looks like this, it now will look like this. Okay? The first cycle, it'll be high, and then the next 3 cycles over here, it'll be low. So you have a high over here and then low over here. Okay. So you can actually implement a state machine that looks like this. Basically, at the edge of the clock, it'll transition over here. At the next edge of the clock, it'll transition over here. And the edge of the clock, it'll go back to 1. And you want this to happen at the positive edge. And the output Y is the divided clock signal. It's 1 only in this case, the first state. The next state happens, it transitions to 0. It stays in 0 for 1 clock cycle. And the next state happens, it transitions to 0 again. It's still 0. And when you go to the next state, it goes back up to Y. Well, this is a simple clock divider circuit. It basically reduces your frequency. So this is actually how you would implement in Verilog. You define first of all your next state as 2-bit registers because you have 3 states here, right? And then you need to encode them somehow. Assume that S0, S1, and S2 are 0. You can use parameters over here to clarify things. This is optional. It's not needed, but it makes reading easier. Now you actually say state 0, state 1, state 2. If you're better at naming, I would say state where clock is high, state where clock is low, 1, and state where clock is low, 2. Of course, it's more cumbersome to read, but that's how it is. Okay, and then you need to basically do what we've done. You basically define your state register. This is our state register. In this case, it has asynchronous reset as positive edge. And it's essentially a D flip-flop. State gets next state whenever the positive edge of clock changes. And we said this already. Okay, we already said that somewhere, you remember. And then you implement your next state logic. Next state logic in this case is very simple. If you're in state 0, so basically it's an always block. Whenever an input changes, you look at the state. And if state is S0, next state is S1. And this is combinational, as you can see. And you get S1, that's next state. If your state is S1, next state is S2. If your state is S2, next state is S0. And at default, your next state is S0. Okay. And then you connect this next state logic into your register. So I'm going to show you the full picture. Basically, this is the output logic. Output logic basically says whether if you're in state 0, S0, Q gets assigned to 1. Because that's how we define our output. This is a Moore machine. In other states, output is 0, right? I mean, as I said, this is a Moore type FSM. And this is basically what we have in the end. This is the entire finite state machine, including the state register over here, the next state logic, combinational over here, and the output logic that's also combinational over here. So it's very simple. Okay, so I'm not going to go through this, but there is also an example of the smiling snail. Now you know who Alyssa Hacker is, so respect Alyssa Hacker, because she's going to appear many times, at least in this book that you read. So this shows the design of I believe, a Mealy type machine, like this type machine for the smiling snail example. Okay, so tomorrow we're going to cover timing and verification. So please read the book, because tomorrow's lecture will be one of the hardest lectures if you've not been exposed to it. But it's going to be fun. Okay.